Are we on? Okay. So, welcome everybody to the last part of the graphical models part of this class. So, what we did on Monday was we started talking about undirected graphical models and the key property in them. And unfortunately, we don't have enough time to prove it. And if you want to see the proof, you can, for instance, talk to me afterwards. It's about a 1 and 1.5 page proof. It's not super illuminating in terms of technique. That's why I'm skipping over it. But it basically requires the Möbius inversion lemma, where you decompose a function of multiple variables into functions of subsets of variables and then basically inversely transform that again. And basically, the Hammersley-Clifford theorem tells us that if I have a joint probabilities distribution where the conditional independence properties are given, can be characterized by this graph. In other words, if I condition on some variables, then the parts of the graph that decompose correspond exactly to the conditional independent parts, then the Hammersley-Clifford theorem applies. So in other words, in that case, I have p of x is e to the sum over cliques psi c of xc minus some g of psi. Okay. The only difference to the slide is that I've just taken the logs and summed it up. There's one tiny little detail that I need to add here. This theorem requires that this condition only holds on the support of the distribution. This sounds like a completely frivolous additional technical detail. You know, why on earth would you want to do something outside the support? Well, it basically needs to deal with cases where maybe that's my domain and maybe here, okay, let's make it really nice off center, is, you know, some point where well, that's not part of the support, then the factorization holds nicely. But if I was to actually use the additional information that I have no data here, then this factorization need not hold anymore. You can easily construct yourself some counterexamples like this. This will come back to bite you if you want to prove things. Other than that, just ignore it. But it's a tiny little detail worthwhile spelling out. And the conditional independence part, so basically if we have a function of this form, that it actually satisfies all the conditions, well, that's kind of very straightforward to prove, because all you do is, if you already have this factorization, then you just separate it into terms belonging to either the separator set and one of the sets of variables, or separator sets and one of the others. And since these are the maximal cliques, I can't really have any overlap otherwise. Right? Because if I had a maximal clique and A and B, you know, owned subsets of one of those maximal cliques, then they would already immediately be connected. So therefore, I would already have a contradiction relative to D separating A and B. Okay. So with that, we now need a little bit more tools. Yeah, this band apparently really exists. Yeah, okay. I don't think you need to listen to the music to know what they sound like. So here's the thing. One of the really useful tools in undirected graphical models are exponential families. We already touched upon them a little bit in the beginning, and we are now going to go back to them with a vengeance, because they make it a lot easier for us to analyze graphical models, conditional random fields, which are just a specific form of graphical models. Basically, all they are is we have a graphical model in some sets of variables, let's say x and y. We condition on x, we want to get the distribution over y. And we just assume that it's an undirected graphical model in the y's, condition on the x's, and then all the machinery will go through very nicely. So all the dynamic programming that we did so far will map over very neatly into this. The functions that we work on look a bit different. The math is identical. Okay. So the first thing that we need is an exponential family. So an exponential family is given by something that looks super intimidating and unwieldy, right? It's e to the inner product between some phi of x and theta minus g of theta. So any density that you can write in this form, e to the inner product between phi of x and theta minus g of theta, maybe after some, algebraic manipulations, is member of the exponential family. Now, why would you care? Because this lets you do certain things much, much more easily. So, for instance, rather than computing expectations, you can just often take derivatives and life gets really, really easy, right? And this has a lot to do with what's called the log partition function, and sometimes also called the cumulative generating function. Okay, so the first thing we need to do is we need to actually prove that this is the right condition for G. Question to the first row, why do we need G? Exactly, we need to normalize, because there is not necessarily any guarantee that the phi of x dot theta might be suitably normalizable. Very good. So, now let's actually work out, and by the way, that's the same G, right? And that's deliberate. So the first thing we need to do is we need to figure out how that normalization should look like, right? So what we have is 1 equals the integral dx of e to the phi of x dot theta minus g, right? Because this is a density, so therefore e to so the integral over that density has to be 1. So now all I do is I just flip this over to the left-hand side, because g doesn't depend on x, so I can get rid of it here, and I have e to the g equals that. So that's very straightforward. Now, since I want to get g, I just get rid of this and use the log. Done. And the only difference to the slide is in the slide I summed over the domain, which is what I need to do in a discrete domain, and otherwise I have an integral. There's actually something slightly more interesting mathematically behind it. So actually what I really need is not just a map phi of x. I also need a measure mu of x on my domain. So if you ever took a measure theory class, this will be totally obvious, otherwise just ignore it. But so an example where this measure actually matters is if I have a Poisson distribution, and the Poisson distribution, as we all know, is defined over the set of non-negative integers. And so now you could just have as a measure the counting measure, so every integer counts the same. But that's actually not what is useful in this case. In this case, you want to have the measure 1 over x factorial. Right. So in other words, very large integers count a lot less than small integers. If I use this with a suitable phi function, and we'll get to that in a moment, then you'll get the Poisson distribution. If you use the same map phi with just the uniform measure, then you'll get a different distribution. You'll get the exponential distribution out of it. So you can basically now play with both mu and phi. Usually we'll sweep mu under the rug because it's just an additional technical detail that we don't have to worry about, because we are not trying to be too formal here. Other than that, yes, that's what you need. Now, any questions about the basic setup so far? Okay, good. So then let's actually prove that those first two conditions hold. Okay. Actually, I'm going to be lazy and probably only prove this one, because that's just takes more space on the whiteboard. So let's do this. So d theta of g of theta. Well, since we have a log here, so this is really straightforward, it's just applying chain rule. So in the denominator we get this big fat integral, and basically dx e to the phi of x of theta. Okay. Now, as said, we are not going to be too formal, so we'll not worry about whether we are allowed to do this, but we'll just pull the derivative into the integral. So there are certain integrability conditions and so on that need to be satisfied, but we won't care. So chain rule applied to this. Okay, well, very easy. It's just again x of phi of x dot theta, and now we have times phi of x here. And so now if you squint really hard, actually you don't have to squint very hard, you can see that this thing here is of course nothing else than e to the g. So I can actually pull that in here. And so what we get is dx of p of x times phi of x. So p of x parameterized by theta times phi of x dx. Okay, so that's exactly what the expectation is. So plugging it in gives us exactly that first line. Now if you take its derivative yet again, you get a little bit more equations, but it's the same idea. You collect, the terms, and then you get the variance, which is rather nice. Okay. So, a really useful property that follows immediately from that is that G is convex. Well, because, the second derivative is the variance. The variance has all eigenvalues greater or equal than 0, so we're done. Okay. So that's very useful. So note, it doesn't generate the second moment here, but the variance. So it doesn't generate the expectation of phi of x transpose, but the actual variance. So let's look at a few examples. And by the way, I strongly urge you to do that second derivation on your own at some point. It's not very difficult, but it'll take you like 5 minutes. You'll learn something. So the simplest thing that I could do is I could have a binomial distribution. And don't worry, I'll go through this in a bit more detail. So in this case, phi of x is x. And x is just, value of 1 and minus 1, let's say. And I'm picking 1 and minus 1 to make the math look prettier afterwards, but you could also pick 1 and 0, and it's just a shift. I could also have a discrete distribution, so in which case, phi of x, and let's just look at what those objects look like. So phi of x for binomial would be 1 or minus 1. For multinomial, it would be the unit vector. Let's say I have 4 different classes, so I have a vector 1, 0, 0, 0, then I have a vector 0, 1, 0, 0, then I have a vector 0, 0, 1, 0, and yes, I should have probably picked only 3 classes, because I'm lazy. So now we have a distribution over 3 classes, and yeah, that's basically how you can get a discrete distribution. What's a little bit less trivial is a Gaussian, in which case we have, x and 1/2 x transposed. And the 1/2 is purely cosmetic to make things look nicer afterwards, because usually when you write your Gaussian, you have e to the minus 1/2, x squared over sigma squared, and that 1/2 is exactly where this comes from. We'll see that in a moment. And yeah, then we have the Poisson distribution, and we also would have the exponential distribution. And they only really differ insofar as, well, in one case the counting measure is 1, in the other case it's 1 over x factorial. So we'll see that in a moment. And then there's a lot more. So the useful thing is you do a Wikipedia search on exponential family, and you'll find a list of probably about 10 to 15 different distributions. Now, you would wonder, what's so special about them, right? I mean, after all, the world isn't necessarily, Poisson or, Dirichlet or Bethe or Wishart or whatever. And when you read a statistics paper, sometimes it's horribly confusing because, they throw all those distributions at you and it's like, why on earth do they pick this combination? So at least that's what happened to me when I started reading those papers. And there's a simple reason. The reason being that there's only a reasonably limited set of distributions for which you can solve a lot of those integrals, like getting your hands on g of phi analytically. And whenever you can solve it analytically, a lot of the subsequent computations are easier. So that's why people like to pick things which are sort of kind of a decent proxy to what they observe, but that's also analytically tractable. In addition to that, there's often something called a conjugate distribution to an exponential family distribution. And we'll get to that in a few slides further on. And what turns out to be the case is that there are useful pairs of distributions and they are conjugates as a prior. Those conjugates will be members of the exponential family too. We'll see that in a moment. But basically, that's why you have the following pairs. And this is something that's fairly useful to remember. Beta and then binomial. And then you would have Dirichlet and then you would have gamma and then you would have Gauss-Wishart for Gauss. And those are essentially the more important pairs. So if you do a Google search for any of those pairs, you'll see dozens of papers coming up with essentially that in the title, or at the very least in the abstract. Just because, sorry.
What are these pairs?
So these are pairs of probability distributions, like, exponential family distributions. Basically, they are pairs of the form where p of x parameterized by theta is x of phi of x of theta minus g of theta. And then there is a prior p of theta given some parameters, let's call them mu naught and m naught, and we'll derive that in a moment, which matches in a suitable way the exponential family distribution. Okay. Wait a few slides until we get there, because otherwise it will confuse you more. And in particular, those priors will have the form that the posterior distribution will be in the same family as the prior. So in other words, if I have a beta prior, then after observing some data from a binomial, I will get a beta posterior. Likewise for Dirichlet multinomial. So if you do Bayesian non-parametrics, you will see a lot of the stuff being used. So before we go into more details there, let me give you a few examples, because this is very abstract stuff. So the simplest case is the binomial, right? Well, we've seen that. Well, phi of x is x, and let's say my domain is 1 and minus 1. So then I can easily normalize, because I have, e to the minus 1 times theta plus e to the 1 times theta. Let's just log 2 cosh of theta. And we already knew that this is a convex function, right? Now, I can go and write out p of x parameterized by theta. And just by plugging in terms, I get this 1 over 1 plus e to the minus 2x theta. Well, this is essentially our logistic. The only difference is that we have this pesky factor of 2 there. Does somebody have an idea how I could have gotten rid of it?
Parameterized by 1/2 theta?
That's almost the right idea. What you'd actually have to do is you'd have to reparameterize phi of x to be 1/2 x. Right? That's essentially how you fix it. There's an alternative parameterization where the domain is 0 and 1. And if you check, you'll see that you can transform those things into each other. Now, a rather nice property of this parameterization of the binomial is that, well, no matter whatever theta I pick, it's going to be a proper probability distribution. It's kind of useful. There's one catch. Which probabilities can I not model efficiently with this parameterization? There are two probabilities that I cannot model exactly. Does anybody have an idea?
Q of 1 is 1.
Perfect. And then the other one.
Minus 1 is 1.
Yeah, exactly. So those two extremes don't work because I'd have to send theta to go to infinity or minus infinity, respectively. So that's a logistic, and I guess everybody's seen one before. As in, you already worked with that in the homework, so I'm fairly sure you've seen it. Now, normal distribution, I guess we've also seen plenty of times. And the more interesting thing there would be to see how this actually interacts with the feature map. For the multinomial, I mean, you've seen this already. By the way, this is exactly what you use in the softmax in a deep network, right? So that's exactly this mapping. And the normalization, the softmax, is exactly this g of theta. Now, well, for the normal distribution, remember, we had e to the, well, let's just say theta 1, because our phi of x was x and 1/2 x transposed. And actually, let's just make it a little bit easier. We only look at scalars here, because otherwise it just looks a little bit awkward. So we have theta 1 times x plus 1/2 theta 2 times x squared. And then we have some normalization g of theta 1 and theta 2. So can somebody tell me immediately a condition that needs to hold for theta 2? There's one that trivially jumps out at you, and there's one that's a little bit more subtle. The subtle condition is actually the stronger one. How about left-hand side of the room? Left to the left of the camera. Can somebody give me a meaningful condition on theta? Hint, the integral needs to converge. Well, what happens if theta 2 is positive? It diverges, right? Well, what happens if theta 2 is 0? Exactly. So if theta 1 is non-trivial and theta 2 is 0, this thing will still diverge. So I basically need to pick theta 2 to be negative enough to make sure that the integral converges. Once you actually go through the algebra here, you'll see that this is equivalent to the condition that the second order moment needs to be at least as large as the first order moment squared. because the variance can never be negative. So remember, when we looked at the variance estimate, sigma was basically the expectation of x transposed minus e of x transposed, and we required that this is positive semi-definite. Now if you just work out the individual terms here, you'll get exactly the condition for the integral to converge.
Isn't theta 2 directly the variance?
Not quite.
Minus theta 2 should be 1 over...
Sorry, yes. So it's...
So this should converge all the time as long as theta 2 is negative, because x squared
Yeah,
is...
if theta 2 is negative, it works, yes.
So we don't need any condition for theta 1, I guess, in that case.
So...
As long as it is negative.
Yeah, yes, but we'll need a condition for theta. But this implies a condition on theta 1. So let's... Well, we can just do the quadratic expansion. So let's have, you know, theta 2, okay, x, and then here, so we get x squared. So we already have a 1/2 here, plus theta 1 divided by theta 2 x. And so now we need to, and we actually have a 2 here, so this works in our favor. And then here we need to add plus theta 1 squared over theta 2 squared. And then I get a, because I need to correct again, basically a minus theta 1 squared over theta 2, 1/2. So now we can, write this out as x plus theta 1 over theta 2 squared. So now we know where the mean is. The mean is at theta 1 over theta 2. You're right. The integral converges whenever theta 2 is negative definite. So in other words, theta 2, well, I mean, for this here, for scalars, it's just that this is less than 0, otherwise it doesn't work. And now in order to make the integral all work out, we need to actually solve this integral, and we'll basically inherit another log term because we need to solve the Gaussian integral. We'll get the log term in the 2 pi's and all of that. This is how we get a Gaussian. Okay. And thanks for correcting me. Thanks. Good catch. Okay, I appreciate that. That means you guys are paying attention. Thanks. Okay, that was probably the most confusing way you've ever seen the normal distribution introduced. The reason why this is actually convenient is because this parameterization in theta 1 and theta 2 happens to be convex. So if you need to estimate mean and covariance in a Gaussian, then going this way is actually rather much easier if I have this as part of a larger convex optimization problem. So for instance, if I have a heteroscedastic regression estimator, so in other words, where my mean and my variance change, then this is the only way to go about if you want to see an estimator that is actually a convex solver. So if you want to know more about that, there's a paper by Canu from, I think, around 2004 or 5. I think it's 5, ICML. I think this was Quark's first paper. And yeah, you can just happily solve this. Okay. So, for the Poisson, I'm not going to go through all the details here, except that we're going to quickly rewrite this in the exponential form. It's usually the Poisson distribution is written as such. So P of x is lambda to the x e to the minus lambda divided by x factorial, which is nothing else than x of x times log lambda minus lambda divided by x factorial. So we already almost have our exponential families notation. The only problem is this, right? So lambda is usually the rate of the Poisson distribution. And what I do is I simply parameterize this as theta. So therefore I get that lambda is e to the theta. And so I get an alternative formulation, x of x times theta minus e to the theta 1 over x factorial. Okay. This is the Poisson distribution now written out in basically normal form for exponential families. Okay. The beta, as you'll see later on, is a nice prior for the parameters for a binomial.
Why isn't the 1 over x a problem?
Because that's just a measure, right? So, as I said, we actually, so this is basically the measure on the domain. So like the Lebesgue measure, you can, if you have a discrete domain, you need to also define, what the weight of, in this case, an atom is. I'm really waving my hands here. I mean, you can formally do that with measure theory, but, and you could either say, well, the weight of my, singletons is 1, or I could say it's 1 over x factorial. It doesn't matter. But each of those design choices may very well give you a different distribution. So, for instance, if we can actually quickly do that, right? Let's say we have P of x, again, e to the, theta x minus g of theta. Okay, so the same thing as in the Poisson, except that now our measure is 1. So then g of theta is the log of the sum of, basically, let's say x goes from 0 up to infinity of e to the theta x. Or in other words, we have e to the theta to the power of x. And so now we all know what that is. And we also know that this only makes sense if theta is negative, otherwise the sum diverges. So it's the log of 1 over 1 minus e to the theta. Right. In other words, it's minus log of 1 minus e to the theta. So this is my log partition function for the exponential distribution. Right? The exponential distribution is one where the mass always decreases, right? Right. Whereas for the Poisson, you can actually have a meaningful mode somewhere. And, to some extent, you are free to pick anything you want as long as it sort of kind of matches the data and as long as the computation is not too intractable. And that's in a way what makes actually a good statistician to pick the right models. Yeah, it's a little bit unsatisfactory, that fact, but that's just what it is. Any questions so far? Okay.
It's like the discrete exponential, right?
Yeah, that's exactly what it is, right? Yeah. Now, it's a very good comment.
The answer to the Lebesgue measure would be e exponential.
Exactly. So, okay, wonderful comment. So let's say we now don't use the... So actually what you really need is you need a measure, right? And you also need a domain. So, and then you need a feature map. Those are really the three things that you need. And so by going from the Poisson to the exponential, we just switch this mu. Now, if I assume, the big measure and I use r plus 0, then this turns into an integral over the exponential, and I guess I'm going to spare you that part, because it's really trivial. But it's a really good comment. Okay, beta distribution, we have that. Well, that's basically a way of, modeling multinomials. So actually binomials in this case. And if you look at that, that already looks a little bit like what you would have if you observed, zeros and ones, right? Because there you'd, raise, the probability of, let's say, the 0 to, some count, and the probability of, ones to the, corresponding other count, and then you normalize it appropriately. So this is actually useful. Okay. Dirichlet is just if you have, more than two possible outcomes, and you now have a distribution over that. The conceptual switch, and it's kind of a non-issue, but it's actually a big deal, depending on how you think about it. Well, this really defines a distribution over distributions. But that's actually what any prior does anyway. It's just here making it really explicit. So in many cases, a prior, is a way of quantifying uncertainty. And, of course, through that, if we have a distribution as the outcome of what we want to estimate, then our prior gives us a distribution over distributions. Now, this gives actually rise to then sometimes something much more fancier. So there is something called a Dirichlet process, where it's not just a simple distribution over, three possible outcomes anymore. And then you are really working on how those measures change the overall outcome. And yeah, computation becomes a really big deal, how to actually do efficient inference there. Okay. So this is essentially exponential families. Okay, let me quickly go to the conjugates here, because actually I think they're somewhat later in the slide. Let me quickly double check. No, actually, I don't have them in my slides this time, but I can just quickly give you an idea. It's there. Rather useful. So, if you think about it, okay, again, p of x parameterized by theta, e to the y of x dot theta minus g of theta. Okay, so if we observe a lot of observations, let's say x1 up to xm, then, well, we'll get that p of that entire set parameterized by theta is just the product of I going from 1 to m p of xi by theta, which, since we have an exponential and the product pulled in becomes a sum here, right, turns into nothing else than e to the inner product between the sum I going from 1 to m phi of xi dot theta minus m times g of theta. Okay. So this is fairly straightforward. What I'm now going to do is I'm going to sneak an m here somewhere. So I'm going to pull the m out. So this of course goes away. And now I need to divide by an m here. Okay. Now this should look a little bit more familiar to what we've seen before, right? This is basically an empirical average of my statistics, right? So I could also really call this mu of x. Right. So except that this average is now, not necessarily the average just over the values of x, but over some features of x, right? So if we were to do maximum likelihood estimation, then we'd get something like d theta of minus log e of x parameterized by theta has to be 0. And of course, what I get is, therefore, that, well, this is nothing else than m times minus d theta of g of theta plus mu of x. Okay. Who recalls what this term here is? Second row from the front. What is it? Second row from the front. Exactly, perfect. This is nothing else than the phi expectation. So now what I get, x drawn from p of x plus by theta. So if I want to set this to 0, what I'm basically getting is this strategy. Mu of x equals e of phi of x. In other words, my maximum likelihood estimate will go and pick the parameter theta in such a way that the empirical observed statistics match the statistics of the distribution that I'm estimating. There's actually a slightly stronger thing going on behind the scenes, and sometimes this is also called maximum entropy estimation for that reason. So max ent. And basically what you can show is that the dual problem to this problem here is that of finding the distribution with the largest entropy for which these specifically chosen moments, as given by phi of x, match the empirical ones. For instance, if I want to find the maximum entropy distribution, so distribution with the largest entropy, that has a given mean and a given variance, I get which distribution? Which statistics do I need for Gaussian? Exactly. And the reason is simply that the Gaussian has as my sufficient statistics exactly x and x squared. And so therefore, this is the corresponding match between max ent of largest entropy for a given covariance. This is sometimes very useful if you want to reason about a more general family of distributions and you don't really have a good entropy estimator, but you can get their covariance. Then you can use the covariance matrix to obtain an upper bound on the entropy. So this is actually rather pretty. Or for instance, if I had a distribution where I have just the first order moment given, then the maximum entropy distribution under that would be the Poisson or the exponential. Okay, so now of course this is kind of weird, right? In one case we have the Poisson, in the other case we have the exponential. What happened? Well, basically entropy again is defined relative to a measure on the domain. And so that's why the entropy is different. The max ent solution is different depending on the measure on the domain. Okay. So, this is estimation in this case. And so for instance, if you take the binomial distribution or multinomial, you'll get exactly the number of counts divided by total number of counts part, right? You can see that immediately because let's say phi of x equals, for a multinomial, it's just the indicator variable. So then the empirical average here is going to be the vector just of fractional counts for, let's say, red, green, and blue, right? So I might get, 3 over 10, 2 over 10, 5 over 10, right? This is what my u of x is going to be, 5 of 10 observations. And so now my condition is that my probability estimate matches this exactly. So of course I'll get exactly a distribution of the 3 outcomes with 3 tenths, 2 tenths, 5 tenths, as my estimate. So it's very easy. Now, of course, maximum likelihood isn't always the brightest thing to do. You may probably want to use a smoothing prior. And the problem with a lot of those smoothing priors happens to be that the posterior distribution may not look very much like what my prior looked like. So more specifically, what may very well happen is that my posterior distribution is in a very different family. But what I could do is I could say, well, let me engineer a prior such that the posterior is in the same family as the prior. And those very distributions that satisfy this are called conjugate distributions. It has nothing to do with convex conjugacy or complex conjugacy. It's just yet another form of conjugacy. Okay, fine. So I'm not going to derive this. I'll just write out what the distribution needs to look like. So if you think about it, we basically had a inner product term in theta, and we had a g theta term in here, right? Those were the two terms that showed up in our likelihood. So now I'm going to engineer a conjugate distribution that has exactly the same property. So p of theta parameterized, let's say by some terms, mu naught, m naught, and I'll explain that in a moment, is going to be e to the, well, let's just say, well, basically we're going to fake a likelihood term, right? m0 times mu0 dot theta minus m0, well, g of theta. And then I need some normalization, h, which depends on m0 and mu0. So the first thing to observe is that now if I multiply this prior with my likelihood, the math works out very beautifully, right? Because what I'll get is m0 gets updated into m0 plus m. And mu0 gets updated into, well, m0 mu0 plus m times mu of x divided by m0 plus m, right? That just follows directly from this and from that. So, have we seen this thing before? We just talked about it, I think, on Monday. Okay, any guess? Any guess where we might have seen this thing before? Where we added pseudo counts. Laplace smoothing, exactly. So Laplace smoothing is just one example of where we used a conjugate distribution to get a nice posterior expression, and also the math works out very beautifully, right? So the nice thing about those conjugate distributions is that using them is trivial. Just compute your statistics, add fake data to it, and then treat the observations plus fake data as if this was all of the data you observed, and then just pretend you're doing maximum likelihood on that. Yes?
What you're saying is that doing MLE plus Laplace smoothing is pretty much doing MAP like a fake.
Correct.
That's it?
Yeah, that's it.
Wow.
Yes. So adding fake data is really useful. This is one of those cases. Yeah. So now the next thing to observe is that this is actually a member of the exponential family, right? If I rewrite things in a suitable way, so what I can do is I can rewrite this as simply the inner product between m naught mu naught and m naught. And now my phi of theta is going to be theta and minus g of theta. Right? This is my phi of theta. Because now it's an exponential family distribution, no longer in x, but in this parameter theta. So here's why this is really useful. Because I can immediately see that this function here is convex. This may be a royal pain in the neck to compute, and I can assure you that Fish will agree with that very much, that it's a royal pain to compute, because yeah, she had to do that more than once for her research. But overall, it's nice and tractable. Here's another nice thing. If I want to integrate out and renormalize the posterior, see, this is already the value of the integral. So if I now want to get the posterior distribution properly normalized, which is usually a royal pain, in the exponential in the conjugate case, it's trivial. Because that is just the h of, then these new parameters plugged in here. So there was a time about maybe 7 or 8 years ago where that simple trick would get you about 2-3 papers. So there's a particularly neat paper called Bayesian sets. And this is by Heller. Heller and Garamani. And then they have some follow-ups on that, on Bayesian clustering or something like that. Some weird title, but it's a very neat paper, which basically all it boils down to, the 8 pages of paper, to the single fact that you can integrate this out nicely. Okay. Unfortunately, the paper's already been written. Okay, so this was fairly math-heavy. I hope it wasn't too confusing. Now let's actually use this a bit more in practice. So the first thing that we can do is we can look at conditional models. And there's really nothing else there except that now our phi of x becomes a phi of x and y. And let's say I want to now get the conditional distribution. I can do that the same way. It's just a conditional exponential family. And now I just have to carry my x around as additional parameter, right? If I want to get the normalization over y. So there's nothing really new there. The notation just gets a little bit heavier. The next thing is, well, I can do estimation. And, well, I showed you one strategy for estimation before, namely maximum likelihood and maximum a posteriori. The alternative is I could just say, well, hey, my parameter theta needs to be small. And so we get something that looks very similar to our Gaussian process, or least mean squares logistic regression estimator, where we have a log partition function and moments need to match, and then I have this quadratic term. Okay. More to the point, we can actually do logistic regression this way. So I'm now going to give you the probably least intuitive way of getting logistic regression. There's a reason, because once you get your head around this, conditional random fields will be trivial. So it's less painful than going to conditional random fields directly. So let's say my phi of x and y is y times phi of x. Do you remember in SVMs we had this kernel matrix, and in support vector classification we had yi, yj, k of xi, xj. That matrix, these entries are exactly the inner product that I get from that. There's a reason I use the same notation, because it is. So, okay, log partition function, that's our logistic, as we had. And this was exactly what we had in logistic regression. So if you were to reformulate this, you'd get exactly the log of 1 plus e to the minus y times phi of x dot theta. Well, modulo this factor of 2. But this is just another way of writing logistic regression. If I use a quadratic penalty, I get exactly quadratically penalized logistic regression out of it. So now we are basically a Gaussian process, logistic regression, with just one line. It's very easy. And then we can predict, and we do this exactly as we would. So very straightforward. Any questions? Because this was a big jump now. Okay. Question to you guys. Second row from the front. What would I need to change if I wanted to make this multi-class? Well, let's start with the distribution, right? So the binary classification for logistic regression, we used the binomial distribution. Which distribution do I need to start with if I want to have multi-class? Discrete, yeah. Basically over k outcomes. So then we remember the statistic that we have in this case would be, let's just already call it EY. So basically this was this vector of 0, 1, 0, 0, 0, 1, 0, 0, 0, 1 that I wrote here before. So now what we have to do is, well, we need to define a joint feature map in phi of x and y. So I have quite a bit of design freedom in this, but I'm going to be lazy today. I'm going to use just a tensor product with some phi of x. Which, by the way, will give me the kernel k of x and y, x prime, y prime, equals delta y, y prime, k of x and x prime. Right? Because tensor products here are products in kernel space. Sorry, the other one. And then, well, I get the corresponding log partition function. Right? So now once I have this, everything else is automatic. I just get the softmax here. I can still impose a quadratic penalty on theta. And now I have multi-class logistic regression. And prediction works the same way. If I wanted the regression, I would simply go and replace the y times phi of x, for instance, by y and y squared, and make the domain of the y's real. And that's exactly what gives me heteroscedastic Gaussian process regression. If you want to have homoscedastic one, in other words, variance is the additive noise is fixed, then I just keep the y's and I change my domain, basically the measure. So there's a lot more that can be done. I don't think there's enough time for me to go into the specific details here, but because I want to show you conditional random fields. So a rather nice thing is that if I have, my clique decomposition, then I have, a exponential families representation, then I can always go and decompose things in such a way that I now only have statistics on the cliques. Maybe after some rotations I can get that. And so basically now, whenever I need to compute the expectations here on phi of x, which is basically what I need for log partition function and other things, I only need to compute the expectations on the maximal cliques. So we've seen that before when we did HMMs, where we basically had the, xi plus 1 and xi yi pairs. And we only needed the probabilities for the singletons and pairs to do estimation. And the same thing happens here as well. It's the same math. just slightly differently motivated. So now for the last bit of the graphical models part, conditional random fields. So let's say I have, don't worry, I'll cover this in a bit more detail as we go along. So if I wanted to have, and there's obviously a typo, this should be phi of x and y, likewise here. Basically what I can do is I could just define, okay, this is my graphical model. So the idea is I observe some x's and I want to estimate what the y's are. And afterwards I will go and condition on the x's and then want to get the distribution over the y's. Right? And my graphical model's assumption is exactly this one here with those edges. So what that means is that the maximal cliques are exactly the yi plus 1 pairs and the xi yi pairs. So these will be exactly the corresponding functions that I need to evaluate to get my sufficient statistics. So I get y1 phi x of x1, all those individual terms. Now I'll get phi y of y1, y2, y2, y3, and so on and so on. And now I'm going to make a couple of approximations. So the first simplifying, because you can obviously write this out like so. The first simplifying assumption I'm going to make is that these potential functions are stationary. Stationary insofar as these functions, which are now functions of yi plus 1, don't really depend on I. So there's only a theta y, and it's the same regardless of where I am. Furthermore, I'm going to assume that these functions are also stationary functions in x and y. They're not stationary in y, but in x and y. So if I observe the same x, I will get the same compatibility score. There's no reason for me to do that, except that it makes the entire inference tractable. A couple of cases where that doesn't hold. So for instance, if I want to do, text annotation, let's say, on news documents, then the headline and then the abstract and the main body of the text will be subtly different. So while I can assume that the corresponding annotations are going to be similar, they're not going to be quite identical. So a better model, for instance, if I wanted to annotate news text, would be to have a model that takes specific care of what happens to the headlines. Now, it may very well be that I don't have enough data to estimate that specific model very well for the headlines, but usually a hierarchical model may be good enough. So if you are doing stuff like this, talk to me later, because there's a lot more tools in there that you can use. But that's basically, the tool set that you use. Now, quite often, just a pairwise assumption like this one here isn't going to be very good. So maybe you have, third order interactions, and then you'd simply get, phi y of yi plus 1, yi plus 2 in here. You need to be modeling this. And if, for instance, you only have, single bits for the yi's, then, 3-bit isn't too hard, right? That's 8 possible values. You need to basically store 8 numbers. That's trivial. So you can actually have fairly long parts here, except that then the dynamic programming becomes a little bit more expensive. And so now, if I want to, for instance, get p of y given x, well, I can do dynamic programming just as before. So we tease out again those functions f of yi plus 1, where these are given like so. And I can use exactly the same algorithms that I implemented before that for HMMs, now for a CRF. Exactly same trick. Okay. Now let's look at examples. So we're going to work through the chains directly. Is everything sort of kind of clear so far? Today was probably the toughest of the lectures, right? There was a lot of theory in there. I tried to go through it reasonably slowly with the whiteboard, but any questions so far? Everything clear? Okay. So I mean, you see this pretty picture there, right? Okay, looks like a sliced result crystal or something like that. Well, not quite, they actually alternate. But joking aside, because you have maybe sodium and chloride opposite. Okay, so anyway, so let's say this is not a salt crystal, but it's actually a graphical model. Where would I use something like this? Can somebody suggest an application to me where such a model...
Image.
An image, exactly. Well, you have the printout, right? Sorry. Yes. So an image would be a pretty good way of dealing with this, because the red guys would be maybe the things that I measure on my sensor. So this might be, the number of photons that I measure there, or, charge or whatever. And the idea is that adjacent pixels probably, with high probability, have, related intensity values. So, for instance, if you look at this is white, there's a good chance that this is also white. Well, it doesn't always hold, because here it's white and there's black and there's white again. But even there, it holds that, for instance, I tend to have lines. So I have to have edges, contours, and stuff like this. Now this is, first of all, a very primitive model, because it's only really dealing with adjacent pixels. So I could use something that has slightly longer range. And there's, however, a really big problem with this. Can somebody tell me what the problem might be with using such a model?
The true width of a grid is the minimum of length and width.
Exactly. So, in other words, we are screwed. So this is basically doing exact inference. This model is hopeless. So, as you can already see now, we now need to take, we need to go back to the approximate inference strategies that I mentioned before, where we had interactable graphical models. And you may very well want to use variational methods or sampling or, loopy belief propagation or any of those tools to actually get a grip on the distribution of those blue dots given the red ones. Just because it's not tractable anymore. And then, once you have this, you can use it in these expectations, right? That's basically where this factors in. To then, get gradients, update the parameters, basically improve the model, and then go and perform another approximate inference step, update the model, and keep on doing this until you're done. So now you see those various bits and pieces fitting together. And that's why sometimes inference in graphical models tends to be very confusing, because it requires a lot of different tools, but it's actually very nice and modular. And what you pick is to some extent a matter of personal preference, or rather, you happen to have a toolbox already around that you can modify slightly and run it. There are some optimality guarantees in some cases. So for instance, if you're sampling and you have a Gibbs sample, then you know that if you run it for long enough, you're going to get the exact answer, which is a really nice plus. But then you may actually pay very dearly computationally. Whereas some other methods, you may not have quite such good guarantees, but then the algorithm is very fast. So now it depends really on whether you have a fast computer. Okay. So let's start with something a little bit less scary than this grid. Let's start with chains. So in a chain, it's a very simple graphical model. P of x is just given by the product of those clique potential psi I of xi and xi plus 1. Okay. So if I observe this, that's fine. Now, let's make this a conditional model. This is exactly what we had with the CRF, right? And so in this case, the giant probability distribution is product of psi I x of xi plus 1 and psi I of xi and yi, right? This looks essentially the same as what we had in the HMM, except that the semantics are a bit different. Here, these functions need not be normalized. So the big difference between the HMM and the CRF is that in the CRF, you normalize at the end. And then in HMM, you deal with lots of terms which are individually normalized, but since as soon as I condition, a lot of this normalization becomes useless anyway, you have to go back and renormalize. So this is why sometimes CRFs are a lot easier to deal with, and this is also one of the reasons why this problem is convex, whereas HMM inference isn't. And so there was a time about maybe 12, 13 years ago when people were really excited about CRFs because they thought this solves a lot of the non-convexity issues that you have in, well, a CRF and HMM. Okay.
What are the drawbacks?
So one of the drawbacks is that you don't have a normalization. The other drawback is that you don't really get a nice generative model of the y's out of this, right? Because in the HMM, we actually modeled P of y given x, right? Whereas for a CRF, we are using a purely discriminative model where we just are interested in, P of x given y. So basically, whatever I said given the observations. And purely discriminative models tend to have better statistical properties. So as in it's much easier to prove consistency and all of that. Here's a small catch to that. Small catch is that a generative model will probably still sort of kind of work if I have perturbations to my data. So for instance, let's say I train my speech recognizer in noise-free rooms where somebody just talks things into the microphone, and then I want to deploy it on a really noisy phone line, it'll be quite awful. Then a CRF is more likely to fail because all of a sudden my distribution changed a lot. A generative model is typically a little bit more likely to recover. But that's really the main drawback. Okay, so now we do dynamic programming. So again, we look at the conditioning parts. We run the messages from the left and from the right. So we've seen all of that before, probably 2-3 times here on the whiteboard. So it's exactly the same thing as what we did before, same machinery. And you can happily run inference on it. Now, chains are kind of trivial. You can do nice hierarchical models. So this is some work that came out of, I think, Microsoft Research Beijing. Now, the web pages came out of that, but also for named entity tagging. So before people went back to neural networks, this was essentially what everybody thought was going to solve the tagging problem on sequences. You guys have a nice hierarchical structure. Now your dynamic program turns into something that's rather much more complicated. And I strongly suggest that you take a class in LTI to look at all the various neat tricks and optimizations and acceleration strategies when you have something that's a more complex dynamic program. So this is, I think, probably the best place to learn this. You might have trees and ontologies. So, for instance, if I want to hierarchically categorize things, then it's kind of more important that I get, let's say, if I have a cute little dog, it's probably important that I actually recognize it as an animal. It's probably a good idea if I recognize it as a mammal. Now, if I confuse this dog with a cat, well, for some intents and purposes, that's the same. But basically, you can see that now with the hierarchical labeling, DEMOS is one of those key examples. The accuracy here matters less than up there, and you may want to have a nice hierarchical model there. And then, there are the spin glasses. So, for instance, for images, and you might want to have long-range interactions. Now, if you do this, it actually works rather neatly. So let's say this is the original image, and then there's some noise added to it, and if you use just local smoothers, you get this. If you use these MRF denoisers, you get that type of result, which looks better than that, better than this. What you would do by now is actually use a deep network and just learn immediately the noisy, noise-free pixel mappings, and it works rather much prettier. So this is the current state of the art, and it's computationally probably no more expensive than this. Another neat thing is you can have semi-Markov models, and yeah, so you can use that for activity recognition and so on. Kevin Murphy had a technical note that came out, I think, in 2005 or so. We actually had a provisional patent filed around the same time, but yeah, basically Kevin actually published the stuff that was good about semi-Markov models. Essentially, if you're modeling something like a traffic light, right, then traffic light has only 3 states, except that it also has a duration and a state. So if I wanted to model this with a hidden Markov model, and I have a clock ticking, by 1 second each, I might have to use a very, very long range or high order Markov model to model a traffic light. Because, for instance, if the traffic light switches after 30 seconds and I have a clock of 1 second each, I have to have a 30th order hidden Markov model or Markov model then to do the inference. Now that's extremely expensive, so you can't really do that efficiently. On the other hand, if I model state and duration, I can do that very easily, right? Because state and duration now, that only grows linearly with the clock, as opposed to exponentially. And the dynamic programming in this case is a little bit more involved, so it's probably about 1 page of derivation, but you can do it. And then you can essentially model both duration length and state transitions. So probably the latest around this would be a paper by Alan Wilsky and Johansson, and I'm probably butchering his name here, and that would be around 2011 or 12, where they use this in a Bayesian non-parametric setting, where they basically have a Dirichlet process equivalent of a semi-Markov model. So this is about as fancy as it gets. Precursor to that would be Emily Fox's PhD thesis. So that work basically used the HMM and ran into exactly the troubles that I mentioned before with the exponential complexity. Whereas the Johansson and Wilsky work used an SMM, and it's much better. Okay. For web pages, likewise, you can analyze it this way. So there's a lot of stuff that you can do. Yeah. So yeah, that's the paper essentially there was a lot of work that came out of Microsoft Research Beijing on that issue. Why on earth would you, by the way, do this? Right? I mean, if you think about it, you have the HTML text. Why would you go and segment it as images? Well, let's just say web page designers use all sorts of tricks to make stuff render in interesting ways on interesting displays. And it's not always very easy to find out from the HTML code what they really want to show up on the screen. So if you doubt that, at some point look at the HTML source code of any of your favorite sites, and it's going to be non-trivial. So in order to analyze this in some meaningfully automatic way, what actually happens quite often is that you would render a web page on what's called a headless browser. So you take something like Firefox or Chrome, rip out the actual display routines, and just have it render the result. And then you're basically doing image or document analysis on the picture of that web page. So this is what often search engines use, also to get around issues like they might have, for instance, in white on white, all sorts of text in there for search engine optimization, right? Which the user doesn't see, but the hope is that the search engine is stupid enough to see it. But by actually rendering the stuff, well, you don't see it either. And so you get something that does relevance ranking based on the visual content as opposed to the link-based content. Okay, so I'm done with graphical models for today. Yeah, this was a lot of material, a lot of ground. I hope that it at least helps you as a guide if you later on encounter graphical models, go back to this and to help you make a little bit more sense out of what you might see. I think the main bottom line is don't be scared. It's a very specific language, and yeah, it's not as scary as the language would suggest. Okay. Any questions? Okay, so next week there's the midterm, aka final. Good luck with that. That's the first thing. Secondly, again, don't be scared. Third, there are going to be more questions than you have time to answer. So don't be scared about this. I think it's a feature because it basically means that you will be able to, to some extent pick and choose a little bit which questions you want to tackle first. So if you get stuck somewhere, look at the other questions, whether you can unstick yourself there first. I think that's good strategy in any exam, regardless. We will try to get a reasonable coverage of all the things that we did in the class so far. I mean, modular this week, so this week doesn't count because you haven't had any chance to really check it with, the TAs and all those things. Yeah, I mean, bottom line is our goal is to make you all succeed, not to kick you out of this class, right? So this is, always keep that in mind. Now, obviously, we cannot everybody award just, an A because they showed up here, right? We can't do that. But our goal is not to be hostile, but the goal is to make sure you succeed. Okay, so do well. Yes?
So, will we part of graphical models? Didn't we do a little bit of that last week?
We did a little bit of it last week, yes. So what I covered last week is in. What I didn't cover last week is not in. So, in other words, there's probably no harm if you know a little bit about dynamic programming, but it's not going to be very deep and detailed. It's probably no harm if you know about EM, right? Also no harm if you know what maximum likelihood is, what, for instance, just, basic estimation is, overall, what happens if I give you more data? Do things get, better or worse? So, just general questions about trying to understand how you operate, some algorithm that maybe you wrote, that maybe somebody else wrote. So that's, I think, going to be quite useful. There will be some technical questions, of course, but there'll be also a fair number of questions of whether you understood what it is. So being able to do algebra really well is useful, but it will not help you unless you actually understand what you're solving. Okay.
There's a lecture that we can miss, manifold.
Well, that's obviously not going to be in the exam, no. Nothing that was supposed to be in the syllabus and we didn't cover will be asked. So the slides and lecture that Banabash and I gave should be sufficient to help you with the exam. Obviously, feel free to bring other handouts, printouts, papers, books, and so on. The limit of 1 foot stacks is simply such that none of you guys breaks their back by carrying things to the lecture, right? And then see you get sued for student abuse. No, but joking aside, I think it'll help you a lot if you make yourself a small cheat sheet, because it'll help you. The preparation of the cheat sheet will help you. The cheat sheet itself might not help you so much, but actually putting everything on one page will help you a lot, or 2 pages or whatever. But it'll force you to digest everything. Okay. Yes.
Will the exam be in this room?
Oh, that's a good question. I think we got another exam room. I think it's on the website. But yeah, okay. So we'll send out another email about this. Yes. Fish, can you handle the exam room issue? Because I'm not around next week.
Yeah.
Okay. Any other questions? I'll try to see that I can put this video up online before I leave today. Anything else? Any issues? So we've deliberately not given you any homework this week so that you can focus on the exam. There will be one more homework after that, handed out essentially with the exam. And that's going to be the last homework. And then for the rest, it's really try and do the most awesome job you can possibly do for the project. Because if you do a good job there, sure, okay, you get a nice score for the class, but hey, fine, whatever. It's not so important. It's not really crazy important for life. On the other hand, if you do a really good job in the project, maybe you'll discover something nice scientifically. Maybe you'll write a nice paper. Maybe it'll help you with your PhD, right? That's a lot more important. Right. This is just providing you the tools. Okay. Cool. So thanks. Would you mind stopping the camera, please?